Okay, my people, hope we're doing well. Video 1 in this review of transformations of graphs dealt with a lot of the conceptual backdrop and the questions we're asking and the procedures and how that all sort of works and the nomenclature we're going to be using. Here we're just going to get into some examples in this video and the next. Examples from classes of functions that you already are familiar with. And the first one, of course, is just absolute value functions. Some teachers begin instructions in transformations with absolute value functions. I know I used to when I was teaching Algebra 2 because it's a really, really simple parent function, and you don't have to worry about the confusion of the absolute value function being coupled with the confusion of transformations. The absolute value function is really easy, and so you can just focus on the transformations. Sometimes teachers wait until quadratics, but if you did not graph absolute value functions by means of transformations, it shouldn't really be all that big of a surprise how they apply. Heck, you can actually talk about the graphing of linear functions using transformations, because the slope, just thought I'd give you a heads up, the slope isn't a tilt of the line, it's actually a stretching of the graph because it's multiplication, right? But I digress. Let's go ahead and let's talk about, I don't know, let's do negative 3/2 x plus 3 plus 4, okay? And so here we have an absolute value function with several transformations, and let's see if we can pause for a second and try and determine for ourselves how many transformations there are. Now we have a c value. There is no b value, but the great thing about absolute value functions is that even if there is, the b value can just be sort of pulled out of the absolute value bars, as long as you're going to go ahead and make it positive, and it can be collapsed into or combined with your a value. So when you're dealing with absolute value functions and quadratic functions, you don't have to deal with the b value, which is kind of nice. You can basically change the form of the function yourself, do a little bit of simplification, and avoid two changes in shape. You only have to deal with an a value. In this case, we don't have a b value. We have a c value. We have an a value that has sort of two aspects to it, right? We have its size, its magnitude, or what we usually refer to as its, ironically enough, absolute value. Its 3/2ness, okay? And then there's also its negativeness right here. And both of those aspects of that number are going to give us two different transformations. And then we have the plus 4. But let's go in order of operations. The plus 3, remember, it is going to require x to compensate for it, and therefore it's going to require x to be 3 units more negative, or 3 units to the left. Now the negativeness of our a is going to give us an x-axis reflection. The 3/2ness, however you want to say it, of our a value is going to give us a vertical stretch of 3/2. Because it is multiplication and it is after the named operation, meaning it's after the absolute value bars are applied, it is a change in shape on the output, and of course that accords with both of those. And then the plus 4 is going to move us up 4 units, and it is in that order, okay? Now let's go ahead and draw the parent function. It's always a good idea because this is the thing that our transformations are being done to. All right, and here's the thing. We can do it in other ways, but just for the sake of being very, very clear and rudimentary, we're going to go point by point, okay? So let's go ahead and take this point down here on the original at 0, 0. Let's move it to the left 3 units. Now, here's the thing. In terms of its output, it's on the x-axis. Its output is 0. So it's going to neither change sign nor increase in magnitude when I multiply it by -3/2, because -3/2 times 0 is just 0. So remember, you can't stretch 0, and you can't stretch 0, and you can't reflect 0. 0 just, when you're multiplying, remains 0. And then I need to move it up 4 units. Okay, and there we go. Okay, let's go ahead and look at, I don't know, let's go ahead and look at 3, 3. Okay, so 3, 3, we're going to move it to the left 3 units. Then we're going to take the 3 unit displacement. I probably should have picked an even number since we have an even denominator right here. And then we're going to multiply it by 1.5, and then we're going to reflect it. And it doesn't matter which one you do first, because multiplication is commutative. You're going to get the same value if you multiply by -1 and then multiply by 3/2 than if you multiply by 3/2 and then multiply by -1. So let's reflect first, since it's easier to reflect 3 than it is to reflect 4.5. And then we're going to stretch it by 1.5, and 3 becomes 4.5 right down here. Okay, let's back up and let's actually do 2, 2, since it's going to be a little bit easier. And let's move it to the left 3. Let's x-axis reflect it. 2 becomes 3 when you multiply it by 3/2, okay? And then we need to move it up 4, okay? Actually, we forgot to move this one up 4, didn't we? 1, 2, 3, 4. And then this one moves up 4 to here. So let's ignore those 2 points right there. Now, the great thing about an absolute value function is that it has symmetry, and therefore we can plot those 2 points on the other side as well. Let's go ahead and take 6, 6, okay? We're going to move it to the left 3. We're going to reflect it down here. Then 6, when you multiply it by 3/2, is going to become 9, and then move it up 4 units, okay? Now, then, by symmetry, this is on the graph as well, and we have enough points. I mean, they are just sort of two linears that are kind of reflected across that line of symmetry, which runs right down the middle. And there is your graph, right? 3/2, remember, is not much steeper than 1, and that's why it almost looks the same as if you had just reflected it over the x and then moved it. It is a little bit steeper, though. Instead of going over 2 and down 2, it's going to go over 2 and down 3, right? And that basically is your graph. And that should be pretty straightforward. That shouldn't be all that surprising. Now let's go ahead and get a little more complicated by reminding ourselves how we do quadratics. Let's do f of x is equal to, oh, I don't know. Let's do 2 x minus 3 squared minus 6. Okay. Now, I have 3 transformations, and the way that I'm going to do this in order is, the first thing, if I were to plug in a number for x, the first thing that I would do is I would subtract 3. That transformation is going to take me 3 units to the right. And then I would square it, and then I would multiply it by 2. That multiplication is going to be a vertical stretch of 2. And then minus 6 is going to bring us down 6 units. Let's go ahead and do our parent. Okay. And that should be sort of automatic. You should remember those values for the parent of quadratics. Sort of sketch it. Remember, it doesn't come to a point. Quadratics are not pointy. They don't look like arrows. Okay. So please respect the parabola. And so there's our parent. And we are going to take each and every point by point, and we're going to transform it. Now, doing it point by point is one way of doing it. Doing it by plotting the new vertex and then stretching it and reflecting it from there is another way to do it, and that's perfectly fine. But since this is sort of just review, it's important that we just go ahead and do it sort of in the rudimentary way. And also doing it point by point reminds us that these equations are indeed what they are is they are shorthand ways of expressing an infinite set of ordered pairs, right? this order pair and that order pair and that order pair and that order pair and that one and that one and that one and that one, that one, that one, that one, and the infinite number of ordered pairs points that are on that curve. So when we pick just several of them as representatives and move them and stretch them based upon the transformations, we're kind of sort of intuitively recognizing that fact. Now, we have 0, 0. We're going to move it to the right 3. Now, a vertical stretch is not going to stretch from here because you can't stretch 0, right? But we can shift 0, and so we move down 6, and we have our new vertex. Let's go ahead and take 1, 1. We're going to move 1, 1 over 3 units. It actually does have a vertical displacement. It's 1 unit away from the axis, and when we stretch it, it goes to 2. And then we're going to move it down 6 units, and there's our point. Now, just like the absolute value functions, these have symmetry as well. Yay, symmetry. Okay, let's take 2, 4. We're going to move it to the right 3 units. It's 4 units away from the axis, so when we stretch it and multiply it by 2, it turns into 8 units away. And so at 8 units away, when I subtract 6, move it down 6, it is now 2 units away. And of course, yay, symmetry again. And if we were to actually do this one, it would be off the Cartesian plane. But let's go ahead and look at it. We're going to move it over 3 units. We're going to vertically stretch it by 2. Now it's 9 units away from the axis. And when I stretch it by 2, it winds up being like 18 units away. And then when we move it down 6, it winds up being 12 units. And so basically it's right about here. And that's nice to know because that means that your graph needs to leave the Cartesian plane before you get to x is equal to 6, right? And so that helps us sort of gauge when it leaves the plane, and it's a pretty significant thing. And our transformation looks something like that. Okay, let's go ahead and do a radical function. That'll be the last one for this particular video. Now, radical function is the first one where we actually have to deal with a b value because when we're dealing with absolute value functions and when we're dealing with quadratics, and let me just go ahead and sort of show this explicitly. If I have y is equal to, 2x minus 4 squared, right, we can basically factor out the 2 in order to show our b value, but we don't want to deal with a b value if we don't have to, and by rules of exponents, that's the same thing as that. So when we're dealing with quadratics, our b value can be transformed into our a value, or be combined. If there's already an a value out there, it can be combined with it. And the same thing with absolute value functions. If I have, x plus 2 over 3 or something like that, I don't have to deal with that as a b value as long as I'm mindful of what I have to do when I pull a factor out of the absolute values, meaning make sure it's positive. I can actually, it's supposed to be 1/3, not 1/2. Transform it into that. And so our b values for these two classes or families of functions, we don't have to deal with them, right? We can do quick simplification and get rid of our b value, collapse it into our a value, or make it our a value if we don't already have one. But when we get to radical functions, if we have something like 2x minus 4, we can go ahead and we're going to want to, right, factor out the b value to reveal our c value. But if we want to transform that into our a value, we're thinking about a vertical stretch of 1.414. No, thank you. No, thank you. It's actually easier to go ahead and reckon with that b value dealing with the horizontal change in shape rather than trying to stretch by a magnitude that is defined by an irrational number. That's just not fun, okay? So what we're going to do is let's go ahead and do something like that. Let's do y is equal to, let's do the square root of 2x minus 4 plus 3. Okay. And, what we're going to do is, like I said, we're going to factor out that b value to reveal our c value. And from there, we actually have 3 transformations, right? The minus 2 takes us to the right 2. That 2 right here, if the radicand is being multiplied by 2, then the x minus 2 value needs to be half as big to get the same output. So what we have is a horizontal shrink, right, because it needs to diminish in value to compensate for the times 2. Horizontal shrink of 1/2, and then we need to move it up 3 units. Now here's the problem. A b value, got to be very careful with it, because this does not necessarily shrink from the axis, meaning the y-axis. Because of the order of operations and the fact that this happens first, and this, of course, we can think of it as redefining where we find our 0 value, right? So when is this radicand 0? The radicand is 0 at x is equal to 2. And so x is equal to 2 sort of becomes our new 0 value, and because of that, all horizontal shrinks and stretches happen with respect to that sort of new axis. And that's kind of why we try to avoid dealing with b values, because sometimes that's a little more difficult to get our head around. But when it comes to classes of functions where we can't sort of simplify away our b value, we have to reckon with it. So let's go ahead and draw the parent function. And of course, it's the top half of a sideways parabola, and it looks something like that. Okay, let me brighten it up just a tad so it shows up well in the video. Now what we're going to do is, let's just go point by point. Let's go ahead and take 0, 0, move it to the right 2. Well, here's the thing, horizontal shrink of 1/2. Now you would think it is 2 units away from the axis, we need to collapse it. But it has actually, the shift has actually redefined where the quote-unquote axis is. This is our new 0 point, and therefore, since stretches and shrinks and also reflections happen with respect to 0, they happen with respect to our x is equal to c line. And in this case, it's not just some vague c, it's actually x is equal to 2. So I move my vertex over 2 units. Since it's what defines 0, it can't shrink because 0 times 1/2 is 0. And then I move it up 3. Okay, let's go ahead and take this right here, this 1, 1. We're going to move it over 2. It is 1 unit away from the new axis, from the new 0 point. And I can shrink 1. When I multiply 1 by 1/2, I get 1/2. And then I can move it up 3 units. Okay, let's take this 4, 2. Let's move it to the right 2 units. It is now 4 units away from the axis. If I shrink it by 1/2, it is now 2 units away from the axis, and I move it up 3 units. Okay, let's take this right here. This is 9, 3. If I move it over 2 units, it's at 11, 3. It's off the Cartesian plane, but fear not, I'm about ready to shrink it. It's 9 units away from this new 0 axis, and basically 9 chopped in half is 4.5. So it's going to go from 9 units away to 4.5 units away, and then up 3. And the next point is not on the Cartesian plane, but it's going to be at 16, 4. Well, 16, 4 can become 18, 4, but 18, 4, then when it's 16 units away. When you chop that in half, it becomes 8 units away. Oh my gosh, right there on the edge of the Cartesian plane. Right about here on the Cartesian plane, and then we move it up 3. And if you think about it, that's reasonable, because notice the progression of horizontal displacement between these points. From here to here is 1/2. From here to here is 3/2. From here to here is 5/2. From here to here is 7/2. And basically, that transformation on the given parent function amounts to that curve right there. Okay, on the next video, we're going to do an exponential, we're going to do a logarithmic, and we're going to do a reciprocal function, okay? As always, please do shoot me an email or a message in chat if you have any questions. Bye.